Okay, 9:14. Okay, so we'll end it. Who are you talking to, right? We'll end at this time. No, we won't. No, we won't, Justin. No, I can tell you right now that's not going to happen. Okay, homework 25 is page 329, section 5-4. Number 3, then numbers 5 through 41 odd. That's a lot. And then number 45. I don't think I need to say anything about 45 because it tells you explicitly what to do. If you're confused about it, just read it again, and there shouldn't be any problems. I think it gives you exactly. You guys should know what's going on with that. But I do want you to do that one. So this is a lot. Did I say through 41? Yeah. Okay. Good. Because you could do 43, and then there's a bunch of word problems. I'm not too concerned about that. Right now I want to get the mechanics of what we're doing today down. But let's start. Let's start with these problems. Okay, so if f of x... Oh, and so it's been a while. Any questions about anything leading up to now?
I don't think so.
Okay, so fundamental theorem of calculus, pretty good with you guys? You get the gist?
Yeah, I think so. Yeah.
Okay, alright, right. So, let's do this first. So, what's the derivative of this function?
Negative sign.
Negative sign, right? Because cosine goes to negative sign, and then plus...
Zero.
Yeah, okay. Interesting. Okay, so now what happens? We take the derivative of this, and what do we get?
Negative cosine.
Negative cosine, because it was negative sine, and so it stays negative, right? Because sine goes to regular positive cosine. But what happens to the 1?
It goes
away. Okay. What about this one? What do we get?
sine x.
Positive sine x, right? Because negative cosine, take the derivative, goes to negative sine. Negative is positive. Okay. So...
No.
Let's say that we didn't know anything about the line above, right? All we know is this, and we want to try to find. So you took the derivative of some function, and we wanted to find the original function. What would you do?
You would know about the 7. But you would just do plus c.
Right. Okay. So what would this be? Forget this, and I said, okay, there's a derivative. So now find its antiderivative.
Cosine of x. Yes.
You would say positive cosine of x, because you know that when you take the derivative of this, you get negative sine, which is what you're looking for. But then, just like Victor said, what we're going to do is say plus c, meaning any constant. And that's true, right? Because you have a plus 7 there. Would it have been any different if you had a 71?
No.
No, you take the derivative of it and it goes away. Ditto if it was 1 over 171, right? It doesn't matter what the constant is. You take the derivative of it, it's gone. And so if you're trying to reconstruct what you had at the beginning, it could have been any constant. And so that's what we mean here. And what this gives us is then what we call a family of functions. Okay, so like visually what's going on here is if that constant happened to be 0, you would just have your regular old cosine x. This would be the case where c equals 0. But c could have been like 5 or something, or 1, or whatever. It could have been another. You change c and you got another function. Let's say this is c equals 2. C could have been negative 2. If c had been, negative 2, then you would have ended up with this. And what we end up with is what we call a family of functions. They all have the same derivative at the same input value, right? Okay? And the only difference is that it's been shifted up and down. I've been hinting at this since the very beginning of the class, right? If you have a function and you shift it up, you have not changed its derivative at that point.
Yeah.
Right? Yeah. Okay. All right. So again, let's play this game. You have a function, you took its derivative, and its derivative was negative cosine x, so its original must have been what? You would say, okay, well, negative sine x. Plus a constant, right? Plus a constant. And indeed, like now, that might look different, right? But you can see that when c equals 1, you get negative sine x plus 1 would be that one right there. Yeah? Now, we're not really going into this in this section right now, but soon enough we're going to see this. Like, that you're going to have this, you'll be given this, and some initial condition. Like, you'll be told that this is true, and we know that g at some point is equal to something. Like, for instance, they could say g at 0 is equal to 1. In which case, you'd say, okay, knowing this, we get this. Knowing this, now we could say, okay, when I plug in a 0, I get negative sine z, exactly, plus c is 1. That's 0 plus c equals 1. Since c equals 1, then we could say, okay, then that original function that we were looking for, the particular solution, given that this is a thing, the particular, this is the general solution, because it could be anything in this family of functions. But now that we're given an initial condition, and it's always called initial condition, and yes, I happen to call it 0, but it didn't need to be 0. Like, I could have given you, like, pi or something, right? And as long as there's something you could, if with one unknown, you just need 1 point, right? This is an xy point, right? This says when you plug in a 0, you get out a 1. So anytime you have one unknown, you need 1 point of data, as I like to call it, to get your particular solution, which in this case would be negative sine x plus 1, which is the same thing as how I originally wrote it. I was just trying to be funky, right? Okay? Everybody got that?
Yeah.
And so we're not doing this initial condition stuff yet. But that's, anyway. So, same thing here. We have some function, and we want to find the original thing. If it was sine, what must the original have been? Negative cosine. This is going to mess you up, right? Like, as you can see, you've been going in one direction for so long. Now we're going in the reverse direction. Every time you're dealing with one of these, with a sine or a cosine, you're going to need to go, wait. And once you do that, since now you're really good at taking derivatives, just take the derivative. And just make sure that you do get that back, right? And of course, plus a constant. If that constant happens to be 5, boom, right? It could have been anything, because when you take the derivative, the constant goes away, and so blah, 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 blah. Everybody with me on that? And since we talked about initial conditions and stuff, I'm going to real quick, let's remember our big example of this year, really, which was that we started at mile marker 100. I think the first one I did was not that, but we have that function right there. Take its derivative, and what do we get?
60.
60, okay. So now let's play the inverse game here. If we have now, forget this, we don't know anything about this. You're given that f prime of x is 60. Therefore, we'd say that its antiderivative is what?
60x plus c.
Plus some constant. And remember at the beginning I said Victor has all the information that he could possibly want except one data point. Where did we start? Right? And check out what happens. If we knew that we started at mile marker 100, that means that at time 0, you plug in a 0, then you get out a 100. And right there, right, you could say, well, plug in a 0, times 0 plus c equals 100. That means c equals 100. And now with that one data point, you could reconstruct the entire record of your thing. So in other words, with a derivative, you miss out on one data, you miss out, but if you get any one data point, you could recover the original function. This is what I'm talking about. So the initial condition gave that to us easily, but what if that's not, what if Noah lost that data point but he had another one. He knew that at hour 1, he was at 160. Well, again,
You could figure it
we could still figure it out because Victor would say, well, here's my record. I know the antiderivative is this. The only thing I'm missing is that. And now it turns we don't have that information, but what we do have is I know that when I plug in a 1, I get out a 160. And so he plugs in a 1, he gets 60 times 1 plus C. So that has to equal 160. Subtract a 60 off, you get C equals 100, which indeed gives us right back to where we were. So that's going to come late, like we'll be doing stuff with that another time, but yeah, it's good to go ahead and talk about it a little bit. Please, please guys, please try to keep it down for me, please. Alright, ready?
Yes.
Okay, here's what we're doing today. So, quick review. Let's get the fundamental theorem of calculus. Fundamental theorem of calculus. We could do this a couple different ways, right? We could say that from A up to B of some function f of t dt is what? How have we been doing this? With a capital F, right?
Oh, yeah. Yes. So then
Capital F of what?
X. Of A. No. Both B.
Of
Yes.
B, that limit
Minus.
that one.
Okay.
Could you please turn that off, Pete? That's a bit too loud for me. I need you guys to be quiet here. And that is where F prime, big F, is little f, right? So we could actually think about it, and this is kind of how I have it in my head, is I'm going to rewrite that as just saying f prime of t dt equals what minus what?
F prime.
It would be this. The antiderivative.
Right.
Right?
Yeah.
Just regular f, right? It means the same thing, and now we don't need to carry along this weight with us. We only did it this way to just kind of make it more general and say, like, this implies that it's already a derivative, right?
Oh, yeah.
Here, it was kind of like, well, let's just make it general. Let's say that we don't know that it's a derivative, and we did a bunch of work and then found, like, yeah, it is. This thing is the antiderivative of this thing. And so, but this is what we, like, this is how we stumbled upon this by looking at our work, right? When we had the f and the f prime, and we started messing with f prime and found this relationship, right? And it's just, yeah, but we changed it up a little bit to make it a bit more general. But let's now write this way. A up to x of f prime of t dt equals what?
F of X minus F of A.
F of x minus f of a, where a is any constant, right? I mean, and we could think about it as a variable, but then you're talking about something with two variables. We're not ready for two variables. Here we're treating x as a variable. But if f is any function, and you plug in a constant, what pops out?
Constant.
A constant, right? So we could just write this like this.
Yeah.
Yeah? Okay? And so this here is this is the fundamental theorem of calculus. Now, each one of these that I've written here is a definite integral. Definite because it gives you two definite endpoints. This one may be variable, but we're specifying what it is, right? And in pictures here, if this is f prime of t, and this is my t-axis, and we have two numbers, a and x, thinking about x as a constant, or a as some constant, some given constant, and x as a variable, then this right here, right, that area from a up to x, is the region over which you're integrating, and then that area is given by this. And that c is going to depend on where a is, whatever that constant is. change A, you're going to change C, because those things are related, but that's not really the point of what we're getting into today, is that what we're going to do is define a new thing. And if we have a definite integral, what other type of integral do you think there might be? A what?
Indefinite.
Indefinite integral. An indefinite integral is just where you don't have these limits right there.
Oh.
And you'll notice, like, this is still
The area under
perfectly...
the entire.
Well, no, it's... Well, yeah, no, because actually the area under the entire thing would be this right here, which we'll get into, which is doable. We could do that. It's just that not right now. Right now, all we're saying is that we have this relationship where you're always going to put some A giving you some C up to some X. So why don't, instead of writing it like that, let's just say, okay, whenever we don't do this, we'll just understand that this simply means the antiderivative.
Okay.
So instead of having to do like I did at the beginning where I say there's some function f and then you took the derivative of it, and then I do this thing like an arrow, like this is all that means right there.
Okay.
And when you do this, we usually use the same variable.
Okay. That happens.
So that's all it means, that this is the antiderivative of this. And so if you do this with some f of x, like with this type of relationship here, then this means this right here. It's another way of thinking about it. And so here we go. I'm going to test your understanding. What's that?
It'd be
Sign
no negative.
just sign.
Wait.
Just
Oh yes.
sign.
Just
You think
sign
it's
it.
just sign?
Yes,
I
it
think
is.
you're right.
Sign of x plus c.
Plus a constant, right? That's all that means. It just means take the antiderivative. And the antiderivative is a family of functions. It could be infinitely many different ones. They all have this part. It's just a matter of how high up or down it's shifted. Okay, what about this?
Negative cosine
There
of
we
x
go.
plus c.
Alright, let's do a couple more. And this, we're going to go through a table that's in your book. These, okay, the ones I'm about to do right now, I'll never remember. Like, I do not remember these. And, like, for at least while you're in this class, it would behoove you to memorize these next ones right here. What do you think?
Oh,
of
now
that?
tan of x.
That's tangent of x.
Plus c.
Plus the
Plus c. Plus a constant. Did you like my joke with the waitress?
oh yes. Yes.
So, okay. Here we go. This is the one. This one I remember fairly well. Now watch out, because secant squared is 1 over cosine squared, right? So 1 over cosine, so the integral of 1 over cosine squared x dx is still equal to tan x plus c. Now, also, secant squared is, let's see if I remember, so sine squared plus cosine squared equals 1. And so if we need a secant squared, I would divide it by cosine squared, cosine squared, cosine squared. So this is tan squared
Oh.
x plus 1 equals secant squared x. And so, therefore, the integral of this, so if you're given something like this, you're going to have to go, uh-oh.
Wait.
I've been giving something I have, wait, did I do that wrong? Yeah, no, sine over cosine is tan squared, okay. So if you're given something like that, you go, uh-oh, I don't know that one. Anytime you have trig stuff, you might want to use, this is why we spent so long doing trig identities. It's like, can I turn that into one of these that I know? And in that case, you could say, oh yeah, that's the same thing as secant squared x.
Which is then tan
which is then, that's, the antiderivative of that is tan x. Why? Because the derivative of tan x is secant squared x, which could be written like that, which could also have been written like plus 1 is cosine squared over cosine squared. And so this could have been written as the integral of cosine squared x over sine squared x plus cosine squared x.
And you do the quotient.
Yeah, well, yeah, you don't do the quotient rule,
Yeah.
ever. And when going in the reverse, it's never gonna be your friend going in reverse. Like, there is no, well, okay, but I'm gonna shut up for now because we'll get into that later.
That was just gonna be lots of trick I didn't.
One thing you'll see me do a lot, and I've already done it, is you notice I put a dx here, I didn't put a dx here or here. I'm just gonna forget to write the dx a bunch. It's always there, and for right now, in our class, all it means is all it tells us is the variable here, right? It just says, well, the variable's x. All right, okay, so said that. Let's do a few more. Here's this is the one. Ugh. Secant x tan x dx.
What is this?
You took the derivative of something and you got secant tangent.
Is that one cotangent?
No. You see, I never remember this. This is why it would be a good idea to remember this one. The derivative of secant is secant tangent. Yeah, I'm sorry. It's just the way it goes. Also, very much like this, we have the integral of cosecant squared x dx.
Cotangent. X.
Yeah. Yeah. It's just kind of nice to see here, right?
Yeah.
Secant and tangent have that because take derivative of tangent, you get secant squared. Take derivative of cotangent, you get cosecant squared. So going in reverse gives you that. And this, see, I don't remember these. So secant tangent, it's cosecant cotangent. What do you think that one gives you?
Cosecant plus C.
I think so. Cosecant x plus c. You see, these are the ones I do not have. Oh no, it's negative. It's
Wait,
such a pain.
Oh.
Yeah, because taking derivative of cosecant gives you negative cosecant cotangent, and so if you have positive cosecant cotangent, it gives you sorry, this is just part of it now. Okay, now. So these are the trig ones, and these in particular are just tough. And I mean, it would just for this you're gonna forget them the way I forgot them. But for this class, it would be really good to go ahead and have at least these 4 memorized. The rest you could read them out, but these are tough, right? It's real tough to get these. But that takes care of all the trig functions, right? Sine, take derivative of sine, you get cosine. Take derivative of cosine, you get negative sine. Derivative of tangent gives you that. Derivative of cotangent, derivative of secant, derivative of derivative of cosecant, derivative of secant, blah 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 blah. Okay?
Yes.
Okay, now here's another one. Antiderivative of x to the n dx. Figure what that has to be.
Nx to the
1 over n times x to the n.
Oh yeah, that's
plus
just the
1.
regular.
It's x to the, so it's x to the
Yes.
what?
N plus 1
N plus 1.
times 1 over n.
Oh yeah.
1 over what?
N. Right? N plus 1.
Let's try it. Let's see what happens. Take the derivative of this.
Oh,
The
it
n
is.
plus 1 drops
Yes.
down. We get that.
It has to be n plus 1.
Aha! Aha! And so, n plus 1, and then
Plus.
plus c, right? And this is like how this is going to work. And so the way that you're going to do this, you're not going to memorize this. The way that you're going to do this is like this. You're going to say, okay, I need 1 power bigger.
Yeah.
And now I need to divide by whatever that is.
Yeah.
Right? And then you add your constant. Okay, so there's the formula for it, but the way you think about it, at least the way I think about it, is, well, I'm undoing derivatives, so it gets bigger. But that constant's not there, so I'm going to need to divide out by it. And this is as long as n is not -1.
Oh yeah.
You can't just pull it, yeah, that ain't going to work. Well, let's try that one. Here, what is that one?
That's 1 over a.
That's the same, and this is how, whenever...
Oh, which is then
Which is natural law.
There you go, natural log plus a constant. So this is the only time when doing integrals, the only time that I don't write this as a power. Because when I see this is locked in my head, right? This is how I think about this, is that if f is log, then f prime is 1 over x. I don't think about it as x to the -1. So the only time that I don't take my integrand, that's the stuff that's in here, right? The stuff that you are in, the function that you're integrating. The only time I don't take that and write it as x to a power is when it's 1 over x. Or 5 over x. What would it be if it's 5 over x?
5 times log of x.
5 times that, because you'd say, well, hold up, there's a constant there, so I'm going to pull that out and then integrate that bad boy. And it's going to be 5 times whatever that is, which is log. And then finally plus constant. Right? And I think you have this in your homework.
You can pull out a 1/2.
You can pull out the 1/2. Exactly. Which is gives you that. Which is then 1/2 natural log x plus a constant. And like technically, really, it's this, but then it's 1/2 log x
Plus 0.
plus a half times a constant,
Which
but
is
it's a
just
constant.
Yeah.
And so one thing we'll say is that the constant absorbs it. Like you could just think, I mean, if you don't know what the constant is, just go ahead and multiply it. It's still constant, right? And so that's what's going on there. Now, one thing about this, I'm not sure how your book would write it, but it might have written it like this. And this is, you know, now is the problem, is that there's 1,000 different ways of writing this. So you do all your work and you get this and you're like, I'm done. Then you check the back of the book and it says this. And you go, where did I go wrong? Well, you didn't. That's the same thing. All right, that's one thing you have to be careful of, because there's 1,000 ways of writing these things. Okay, all right, so that's one. K is a constant.
0.
Dad.
Wait, no, sorry. That'd be the derivative.
It would be
You're right.
K squared. No.
k times x.
Yeah. There you go. Yeah, and this, now we're undoing, we're going in the opposite direction that we've been going all year. So this is where, and this is why I suggest you do this and forget everything that you've just done. Now take a derivative of it. Take the derivative of it, and what do you get?
K.
K. Is that what you had?
Yes.
Okay, good
So
to go.
the antiderivative of 0 is just a constant thing.
Oh.
Yeah.
Okay.
Constant. Exactly. Good. Good reasoning. Yes. Yes. That is true. Because what's the slope of a constant? Of a constant function? It's 0. Right? If I said f of x is some constant, it looks like that. See? Its derivative would be 0. And so integrate 0, you get back a constant. Good. Okay. And so, I did want to talk about that. And of course, like we talked about last time, the integral is a linear operator. So if you're integrating a f of x plus b, say g of x dx, then we could split this up because it's addition. We could say it's the same thing as integrating a times f of x plus the integral of b times g of x.
Pull out the A.
Then you can pull out the a and the b, because it'll probably make your life easier, and I have an example to show that that is the case. And you'll notice I've dropped my dx completely. I don't mind if you drop your dx. That's cool. I mean, it's a bad habit, but if you're doing it in calculations, I'm not gonna bother you for that. So just know that eventually it'll matter, especially when you start doing double integrals. Then it matters. Because you have some function, double integral happens when you have a function of two variables. And you're integrating with respect to both of them. So let's say in x you're going from 1 to 2, and in y you're going from, I don't know, 7 to 9. Now it matters, and you need to know which one you're doing first. And it's like, this is an integral, and then there's it's an integral and an integral.
You have an infinite amount of integrals. Like infinite.
With infinite
Like an
variables.
infinite sum of.
An infinite sum of infinite sums. I've never seen an infinite this way. I don't see why you couldn't. Have I seen it? I don't know. I've not run into that. Would not be surprised if there is. I mean, yeah.
That'd be
So,
a pain to write.
you could probably formulate it a little bit differently. So here's an example. Okay, so let's do this one. I wanted to do, how did I have this? I had it as, I didn't write it down. I think I had it as, yep, that was it. Now you're thinking, okay, quotient rule.
We can split it up.
Split it up. How do you want to split this up?
F of x over x squared minus 3 over x.
5x over.
Then we can
Yeah.
cancel the x.
So 5x over x squared minus 3 over x squared.
Yeah.
That's going to make life easier. Okay, so I'm going to go ahead and write that as 5 over x minus the integral of 3 over x squared. Are there other things we could do to make life easier?
We can make
5
it
over x
x to the negative 1 times 5. And then 4.
You could do it as x
Oh,
to
it's
the,
just-
that's the only
It's just
time.
1 over x times 5, and then it's what should be
Or how about, I'm going to pull it out this
Yeah.
way. This is how I like to do it. And then what about this one?
3 times integral 1 over x.
Yeah, and don't forget the minus. 3, 1 over x squared. Now that one,
Is
5
natural
times
log.
log.
that's natural log. So let's just go ahead and get rid of him because he's easy to deal with. Now this is 3. I'm going to suggest, so given that that's the 1 over x, that's the only time I've said, and I've said this, right? It's the only time that I'm not going to rewrite this as x to some power.
So it'd be x.
Okay, so here we go. Now I'm going to write it up here. I'm going to copy this down. In fact, I'm going to copy this down so we can see, I want to be able to see it like this.
Negative 1.
over-
Negative times x to the negative 1.
1 over x to the
Minus
negative
3. Now check this out. We have you have a negative here. I'm going to suggest that you do something like this. That's just going to make your life easier because it's 3 times whatever this is, so you better do something like that. So 3 times this right here is, so what is it? It's x to the what?
Negative
Negative 1.
negative.
So it's
Negative.
negative 1 times
Yeah.
x times.
So, and then it would be 1 over negative 1, or I could just write that as negative.
Yeah.
And this is why that parenthesis is your best friend, because it's a negative negative tells us, okay, 5 log x. Negative negative is plus 3 x to the negative 1 plus constant, which we could rewrite as this, if you like. And then we're going to check it. Let's check it, okay? Because I'm telling you, I suggest you do this. Okay, so what's the derivative of this?
Well, it's 5 over x.
5 over x. What's the derivative of this? So that's 3x to the minus 1. Minus 1 comes down.
Negative 3 to
Negative 2. Yep.
Yes.
Negative 3x to the negative 2. The constant's gone. So we have 5 over x minus 3 over x squared.
Yeah.
That looks nothing like what we started with.
We can
Oh
combine a
no. Oh, okay. Okay. So this is what I mean, right? Like, same thing like when we were doing derivatives. This is, don't think about quotient rule, but like, if you have something that's complicated, if you split it up, like just like we did with this, right? Like at the beginning of class, like at the beginning when you first learned a derivative, you'd look at that and go, uh-oh, what's the slope of that thing? No, just break it into little bits, right? We just look at that part. We don't think about this, we just look at that part, right? Same thing here. Can you break this up so that you could, so that it's manageable pieces, right? Turn something you haven't seen before into something you've seen before, right? That's the idea here. I've been saying that for like 2.5 years now. Like, take a problem you haven't seen, like that's the name of the game with math. Turn a problem you haven't seen before into a problem you've seen before. So that's that. I didn't assign any homework on, it's called the net change theorem and like total distance traveled and stuff like that. I have a feeling that we'll get plenty of it, but basically I do want to do this. So, alright, this is going to be cool. So, does anybody remember the formula for projectile motion? That is, like if you drop something or like you, let's say, remember, you take a ball and you throw it up at a certain initial velocity.
It was a parabola.
It's a parabola, right? Does anybody remember the formula for it in terms of t? It's a parabola, and so we know that it's t squared plus something t plus something. Does anybody remember what that bit is and what that bit is? And what that bit is, actually. Now, so it's
Just a guess.
1/2 the acceleration. This is the initial velocity, and this is your initial position. In fact, I'm going to rename this P for position. And we just, in Algebra 2, we just magicked this out of nowhere. We're like, trust me, it's equal to this. And it's, hey buddy, can you keep it down, please? Can we try to be quiet? Okay, and so let's derive this. This was given, please. Thank you. So this is given constant acceleration. That's the key, right? You have a ball, and you throw it up with some initial velocity. And the only force, as soon as it leaves my hand, guys, please, quiet. As soon as it leaves my hand, the only force that's acting on it is gravity. And it's acting in the downward direction. And so we're going to give it a sign. We're going to say that the acceleration of gravity is negative 9.8 meters per second. But I'm just going to call it A. And as a matter of fact, this formula worked out to be minus 4.9. Like that. That's just what they give you in the book. And then whatever the velocity is in meters per second, and then whatever your initial position is in meters.
Yeah.
Okay, so let's derive this. If acceleration is 9.8 meters per second, stop, please stop. Please be quiet. Can you guys go into Vinny's room, please? Go on, go with Peter. Go with Peter. Okay, so if my acceleration as a function of time is constant, and for right now we know what it is, but we're just going to say it's A. Acceleration is the derivative of what?
Velocity.
Velocity. And so you're telling me that the antiderivative of acceleration is velocity?
Yeah.
So the antiderivative of acceleration is velocity. Okay. We're gonna keep this okay, so this is just a constant. So A dt. What's the antiderivative of a constant A? Is it 0? antiderivative.
X, KX, CX.
Is it x?
A, T. AT.
Aha! And now, okay, AT plus a constant,
Yeah.
right? So now let's check it. Check it. Okay, we have some function AT plus C. Take its derivative, and what do we get?
P. A.
A, right? Okay.
Yeah.
All right. Okay. So that's good. All right. So okay. How do we find that constant C?
You need a point.
We need a point. We need an initial velocity. So in other words, if we knew what the velocity was at time 0, and let's say that we did, say it was 5 or 7, why don't we just call it whatever the initial velocity is, just like it shows up in the formula. We'll just call it 0. Okay. So if v of t is equal to at plus a constant, then when I plug in a 0, I get 0 plus c. So that constant must be whatever the initial velocity is, whatever the velocity is here at time 0, right? Okay, so let me go ahead. I'm going to rewrite that right here. And does that make sense?
Yeah.
Like that your initial velocity, if you have a function which tells you the velocity, that whatever that function is, when if you plug in a 0, that the initial bit is that right there, right?
Yeah.
So if we're thinking about, here's my v of t, and you want to know what's the time at 0, well, that's going to be that intercept right there, right? And we're just calling it v0. It could have been 5. It could have been -7. Who knows? But that's what's going on here. Okay. Okay. So we're all good on that. But velocity is the derivative of what?
Accelerate.
No, position.
Position. So, okay. So if you take the derivative of position, you get velocity.
Yeah.
So the antiderivative of velocity must be position.
Yes.
Right? And that's all I'm saying here. And this is the fundamental theorem of calculus here, right? The antiderivative of a derivative is the original thing,
Yeah.
plus a constant. And so, and we just said that velocity is the derivative of position. So, position, t, is equal to the antiderivative of the velocity. So, the velocity is this, at plus some constant, dt. Can we split this up? Can we make this easier?
Yeah.
It's
So
integral
of AT plus the
integral of
at plus the integral of v0. What's the variable here?
T.
T. So can I pull anything out?
Plot an A.
A t dt plus, well, it's just a constant. Okay, so then what's the antiderivative of t?
A times
1/2.
A
times
times
1/2
t squared.
Yeah.
And then what's the antiderivative of a constant?
T. Right.
Yeah.
V0 times T.
The
plus
v0
C
times t plus
C.
a constant. So let's see what we got. P, the position, time is 1 a times a half, or how about 1/2 times a? T squared plus v0t, your initial velocity, plus t, plus a constant.
And the constant.
And the constant, how do we find the constant? Well, if you know your initial position, we could say your position at time 0, we'll just call that my initial position, we'll call it p0.
Yeah.
And so when I plug that in, I get p, I get a 0 here, plus a 0 here, plus a constant, which I'm saying, whatever it is my initial position, and so,
Yeah.
there it is, right?
And if A is 9.
And if A, and so we have P of t is 1/2 the acceleration times t squared plus the initial velocity times t plus the initial position. Now we get negative, A is negative 9.8, so 1/2 negative 9.8 t squared plus the initial velocity,
Negative 4.9.
which is negative 4.9. That's why the book says, trust me, it works, but now we can prove it.
So we were really doing calculus.
We were doing calculus the whole time. There it goes. And then like they give you one of those, and then they would say, magically, the velocity is equal to negative 9.8 t plus v0. It's like, yeah, it is, right? You take the derivative of that and you get that. Ah, that's interesting, right? And so that's where that comes from. Now we proved it, that free fall motion, or it's not just that. Like an object in free fall is a special case of constant acceleration. That's all we assumed at the beginning, was that the acceleration on this one thing, whatever it is, in whatever direction it's going, whatever, that acceleration is constant. Therefore it moves like this. That's why it moves like that. Because acceleration is the derivative of velocity. And velocity is a derivative of position. So you take the antiderivative of acceleration, you get velocity, you take the antiderivative again, and there you go. So there's that. Now let's do a ton of examples. Let's see how we're doing on time. Oh yeah, we're good. Okay, number 24. Okay, so you're also going to be doing definite integrals here. And so let's do an indefinite integral. This is number 12, and it is u squared plus 1 over u squared du. They put parentheses here, I'm not going to bother. Okay, what do you want to do?
Split it up.
Just take the integral of
So something like this?
Yes.
Okay. Now, in practice, you're probably not going to actually write this step. Same way like with a derivative, if you're doing this and you want, you probably wouldn't write this, right? Like, you just do it, and so that's cool. Although, if there's constants involved, your life might be easier to take this step. We'll see an example of that in a minute. So what's the antiderivative of this?
1/3 u
There you go.
cubed.
There you go.
Yeah.
What's the antiderivative of that?
X. I mean,
Or-
u.
Careful. Okay. Now this, I would go ahead and write like
U to the
that.
What was that one? It was
Negative u to the
negative u
negative
to the
one.
negative 1.
Negative u to the negative 1 plus a constant. There you go.
Yeah.
All right. Easy enough. And it might look different in your book, right? If it does, keep going with it until it looks the way it does in your book. Okay. Yeah, and so antiderivatives are just, ooh, good luck with that. So, let's do this one. This is similar. So, now here's a definite integral. So we're going to do a definite integral from 1 to 2 of y plus 5y to the 7th over y cubed dy. Okay, the idea is if we could find its antiderivative, whatever that is, then we're going to plug in a 2, and then we're going to subtract off whatever it is at 1, and we have that nice way of doing that we find the function and then this to remind us of what we're doing. That's how I like to do it. I'm going to find the antiderivative and then write it like that so that I don't forget. I still have more work to do, and those are the numbers I'm plugging in. So let's find that antiderivative. What do you want to do with this? This is very similar.
Integral of 1 to 2.
Split it up. So of
y over y
y over y to the 3rd
plus
5y
5y
to the 7th over y cubed.
5y to the 7th, y to the 3rd. Okay, so this is the same as
1 over 1 squared
that.
plus 5y
5y over to the 5y to the
4th over, yeah.
this one.
Yeah?
Yes.
Yep. And then,
Okay.
which is y to the negative 2.
Yeah, there you go. Y to the negative 2 plus 5, and this is y over
1 over 5.
4.
Yeah.
Y to the y would be...
Now we can take antiderivative.
Okay, and so antiderivative of that.
Negative y.
Negative y.
1.
Negative 1. Yeah.
There you go.
Plus
Plus 5 times
1 over 5.
1/5.
Oh,
1
y
fifth.
to the 5th.
Y to the 5th.
Yeah.
Plus a constant.
Yeah.
But, and here's the thing, that plus a constant part, like, instead of doing that, I do this.
Oh, okay.
When you're doing a definite integral, right, because I mean you could do plus a constant,
But you
and
don't-
then the constant, when you go to subtract them, right,
They just
it's
go
going to go away,
Yeah.
right? Like if you found that your antiderivative was this, and you wanted to evaluate it at 2 and 1, you would have, okay, you would say then, okay, that's the same as 2 squared plus a constant minus 1 squared plus a constant. And so it's really redundant to write that minus 1 minus c, because the constant's always going to be gone. So when you're doing a definite integral, I mean, it's true that the antiderivative includes some constant, but it's always going to be gone. So when you're evaluating them at endpoints, you might as well not even write it. You're just going to waste your time. Right? Okay, so I'm going to actually rewrite that one more time and say, okay, that's the same thing as negative 1 over y. Those are gone, plus y to the 5th, evaluated at 2 and 1.
Yeah.
So that's, parentheses are your best friends when you're doing this, because there's negatives involved and blah, da, 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 da. So negative 1 over 2 plus 2 to the 5th is, I think, 32.
Yeah.
Should I sound right?
2 to the 5th. No, wait. No, it's 60. No, it's 64. It shouldn't be 32.
This way, okay.
Oh wait, is it there? It might be. You're right.
16.
Yeah, you're right. Sorry. Yeah.
32. Hey, how many times have I been wrong about, like, what's 5 times 3? I don't know, man. Okay, then we plug in a 1. We get negative 1 plus a 1. Oh, that's nice. That's a 0. So this is just 32 minus a half.
Yeah.
I'm not going to bother. Okay, so there you go. All right.
63.
That's how you do these. Let's do a couple more. Oh boy. That doesn't sound good. Oh, okay. Yeah, we do need to talk about this. I'll give you one. This is similar to 41. Let's do the integral from negative 1 to 3 of 2 times the absolute value of x minus 1 dx.
Oh, we did something.
So, here's the hard part. First off, I want to break this guy up.
And get the 2 out.
Take the 2 out, right? And now, this is a little bit more manageable. So, the antiderivative of this, that's easy.
Yeah.
This guy is rough, because let's just think about what he looks like, right? So absolute value of x does this, yeah?
Yes.
Yeah.
So from negative 1 up to 0, he's one function. And then from 0 up to 3, he's a different function. So what I'm going to do is say, okay, whenever it's negative, this thing, now watch, because it's 2 times whatever that amount is.
Yeah.
Okay, and so minus, what's the antiderivative of 1? dx?
X. So negative x plus c.
And we're evaluating, but we're evaluating it from 3 to minus 1.
Yeah.
So you could put plus c, but nah. Okay, so this thing is the same thing as integrating from negative 1 to 0 and then integrating from 0 up to 3, because this is the picture I have in my head, right?
Oh, and it's negative x.
Negative 1 up to 0 and then up to 3. I'm going to take the two, where they're two different functions, I'm just going to split them into two different things. And over here, what's the function?
Negative.
Negative x. And over here
Positive
is just positive x. So what's the antiderivative of negative x?
Negative 1
X to the
x
x
squared.
negative. No.
Negative 1/2 x squared.
I think so. Let's check it. Right? Right? So the 2 drops down, kills the 2. Negative x to the 1.
Yeah.
Negative x to the 1. Okay, so negative 1/2 x squared evaluate 0, negative 1.
Okay. Yeah.
Okay? Alright, that's kind of how we're doing this. When there's definite integrals, you find your antiderivative. Instead of plus c, you do this little trick. And that's going to help you. It's going to help a lot. It's the antiderivative of this.
1/2 x squared.
1/2 x squared plus c, but instead of plus c, we're going to go from 3 to 0. Now let's go ahead and evaluate this. This is x evaluated at 3 and negative 1. So that's 3 minus negative 1. Parentheses are your best friends. So that's the same thing as minus 4. I'm going to save myself a little room and go minus 4. Okay, now let's go up here and go equals 2 times. This thing is 0 minus, plug in a negative 1,
Times.
Yeah.
still
one.
negative 1/2. Okay, plus
Plug in a
3, so that gives us 3 squared is 9. So 9/2 minus,
-0.
plug in a 0 is 0. Okay, minus 4. Parentheses are your best friends here.
It's 1/2.
That's just
That's
1.
1/2 plus
10 halves.
9/2 minus 4. That's 10/2.
5.
But then it just goes away. So it's
Just
just
yeah.
wait.
Wait.
Oh,
Wait.
whoa.
Wait.
Thank
yeah,
you.
because it
Thank you.
Yeah.
Thank you.
equals 6.
6. Yeah. 10 minus
Yeah. Yeah. All right. Yeah, absolute value is the bane of everybody's existence. And the way you deal with it is just say, hold up, what does this thing look like? It looks like this. That's, yeah, it's similar to 41, not quite the same thing. Okay, I did want to do one of these. Yeah, okay. All right, all right. Here we go. 30 is the definite integral from 1 to 2 of x plus 1 over x squared dx. What do you think you want to do with that?
Multiply it out.
It's probably going to be anytime you have a polynomial, right? And you have some others. I wasn't going to go over these, but it's just the antiderivative of stuff like this, like 2u plus 3, and then like it was like u minus like 3u cubed or something like that. It's going to be easy because same thing like you know with derivatives. It's just easier if you multiply it out and do it bit by bit. Right? So that's what I'm going to do here too. So first outer inner last gives us what?
X squared plus 1 over 2 over x squared.
No, the x's go away, right?
Yeah,
Just
yeah.
2.
Let's.
It's just 2, I think.
So outer gives you that times that, which is 1. Inner gives you that times that, which is 1. So it should just be 2. Okay.
Plus 1 over
And then what is it? Plus
1 over x squared.
1 over x squared. So that's the same thing as this,
Yeah.
right? Antiderivative of that.
1/2, 1/3, 1 cubed x cubed.
Yeah.
All right.
Plus 2
x, just
plus x plus 2x.
And
Oh,
then
2x.
this is the same thing as that.
Negative x to the negative.
Negative x to the negative 1.
Yeah.
All right.
Those are all valid.
And they're all going from here to here, or from there to there. So let's just check it. Take the derivative of that, do you get that? Take derivative of that, do you get that? Derivative of that,
Yeah.
and negative 1 drops down, negative 2, that's negative 1 over x squared. Now positive 1 over x squared. Negative. Yeah, because of the negative. Okay.
Yeah.
Yeah, see, good to check. Okay, all right, so now I'm going to evaluate that 2 and 1. So 1/3 2 cubed plus 2 minus 1 over 2 minus 1 1/3 plus 2 minus 1. Let's see if we can do anything tricky here. So this is 8/3 minus 1/3.
7/3.
This is 4 minus 2 is
Just
2.
2.
Negative minus minus, so that's
3/2.
plus 1.
Yeah.
Yeah, this is the hard part. The algebra is the hard part of this. I've said this for a long time now. I mean, it's funny that, like, the thing that's going to mess you up is stuff like this. And yeah, it's funny. So 7/3 plus 2 plus a half. That's something. Who cares?
So instead of evaluating them each individually, like doing 1/3 x cubed from 1 to 2 plus, like you can just evaluate them all at once, and then.
Well,
Because right now the brackets it's like.
wait. I thought you were saying something else. Say all of that again. I misunderstood you.
So you could also like do this by kind of like factoring in the evaluate sign, so doing 1/3 times x cubed, evaluate that from 1 to 2, then plus.
Yes, you mean each one of these individually?
Yeah.
Yes. So each one of these could have been like this.
Yeah.
If it's easier. Sometimes it is, sometimes it's
But
not.
it's the same.
It works out exactly the same way, right? Because let's think about this. You have f evaluated from b to a plus g evaluated plus h evaluated b to a. So that's the same thing as saying fb minus fa plus gb minus ga plus hb minus ha, which is the same thing as f of b plus g of b plus h of b minus f of a.
Plus FG.
We're also minusing off a g, so I have to add it because I'm minusing it. Minus h of a. Let's just check. The minus comes over and gives you a minus. Minus comes over, gives you a minus. Minus comes over, gives you a minus. Yep, so that's the same thing as f plus g plus h evaluated at b. Oops. Yeah. F plus g plus h evaluated at b minus that evaluated at a. Yeah, okay, I see what you're saying. And yes, and sometimes, like, which one's easier? Right? Like, sometimes you get cool cancellation, and it depends on this also. Like, like one of the best case scenarios is if you have this, because, well, except in this case, can you have a 0? So that's another thing to kind of keep in. Well, we don't need to worry about it quite yet.
Because it blows up there. So
The original function would blow up there, and so if you're trying to integrate from there to there, the original function blows up there, and so you're trying to find the area where it blows up, and you're going to find out that that's going to blow up. Right? It's going to happen, right? But in the case where it doesn't do that, 0 is your best friend because you plug in a 0 and it's just you forget about it, you don't even bother. Right? Okay, you guys want to see another one, or you guys want to get out of here?
We can do one more.
All right, let's do one more. Let's do this wicked looking one. Okay, 36. the integral from 0 to pi over 3 of sine theta
Oh.
plus sine theta tan squared theta all over
Oh,
Yeah.
secant squared theta
well, then I'm already starting.
d theta. Now,
Just split it up.
yeah, and that's probably what I would do. And it would be really nice to, like, as you're doing that, have this on page 325.
Yeah.
Just have it in front of you,
Yes.
so you can see. Wait a minute, am I there yet? Do I have one that I know? Because the idea is turn something you haven't seen before into something you've seen before. And so I'm gonna. That's what I'm gonna. The whole time I'm gonna be thinking, have I seen this yet? And so yeah, let's split this up. This is the same as sine over secant squared plus sine tan squared over secant squared. Maybe get everybody in terms of just sines and cosines, and maybe stuff will start canceling out. I don't know. But wait, sine over secant squared, that's the same as sine times cosine squared.
Oh yeah. That help.
Will it? I don't know. Let's see. So,
But you could do
unless...
that to both of them.
Now I'm looking over here, secant squared sine. This is looking pretty dire. So,
Wait,
this
secant
is the
squared
same
equals, what did we say? It's just tan, right?
Tan of x.
This is the same thing as sine times cosine
So we could
squared.
get one of the tangents to cancel in the second one, because secant squared is...
Right, and so let's see. So this, I want to actually write this one out. This is sine squared cosine squared over 1 over cosine squared. Yeah? And so that guy comes up into the numerator, right?
and cancels one of
And
these.
cancels one of those. So that gives us, so sine cosine squared plus
Sine
sine times sine squared.
over cosine squared. Over
Just
cosine.
the sign.
Oh, no, never mind.
Oh yeah, because that
Yeah.
comes up and kills
Yeah, yeah.
him. Right.
Yeah.
Yeah. Okay. Now I'm looking and I'm not seeing anything in my. It's funny because in like the next, I think it's the next thing we do. Let's see. What is it? Let me just see what the next section is. Yeah. Because in the next section.
Oh, you can
there's-
factor out a sine and then it's cosine squared plus sine squared. And
There you
then
go.
it's
There
1.
you go.
Yeah.
There you go. So that works out really well. However, next sector, you're going to have stuff like this, but that's not going to be a possibility. And it's super easy to deal with when you have, well, the next thing that we do. There's a method for dealing with stuff. Like this one happens to be the case that you can pull out a sine.
Well, if you have it all in sines and coses, it's not that hard to take the antiderivative, right? It's only, or if it's,
But it's sine squared.
No, it's wicked hard. It's because this worked out that now we could do this.
So just the equals sine.
which is,
Yeah.
So this works out to what?
negative cosine.
Negative cosine x evaluated
From
0 to pi over 3. Now let's just see. Let's just make sure. Take the derivative of negative cosine, and you do get positive sine. Okay, so our sines are good. SIG and S. Our sines are good. So now, okay, I'm going to evaluate that. That's negative cosine pi over 3 minus negative cosine 0. Now, cosine pi over 3. Let's just see. This one is pi over 3. This is
So,
1,
1
2.
over 2.
Yeah.
So, let's see. Right, so 1/2.
Negative
So
1/2 plus 1.
negative 1/2 minus negative cosine 0 is 1, and so that's the same as plus 1, so this is 1/2. Please use parentheses with all this, because as you can see, negatives, and you'll have negatives of negatives, and then something that doesn't look negative will turn out to be negative, right? Because like had this been what, like 4/3, that would have been a negative of a negative, and a negative would be negative, and positive, and negative, and yeah. And so, it's just a total pain, right? So, now, it's funny because, like, my instinct, as soon as I saw this, was to make it 10 times harder than it needs to be. And it doesn't need to be that hard, but like you're gonna learn this trick next time on Tuesday. We're gonna learn another method. Basically, there's 1,000 methods for dealing with integrals. You've been given really simple ones. There are wicked hard ones, and if we got a few minutes, I would like to talk about one more thing that I wanted to talk about. But like integrals are wicked hard, and there's like. Because, I mean, you could think of, like, what you took the derivative of a function and you got this. Well, what was the original function? Yikes. It's just like multiplication's easier than division, right?
Yes.
And ditto, differentiation's easier than integration.
Yeah.
Oh, man, there's a couple things. You guys got a few more minutes because there's a couple more things I wanted to talk about, actually.
Yeah.
Okay, all right, great. Okay, so one of the things is... So, differentiation and integration are like inverse operations, right? Like if you take a function and you integrate it, and then you take its derivative,
You just get the
you
original.
get the original thing back, right? This is now... When we're talking about inverse functions, right? We say, all right, you plug in some value, and you get, you take an x, and you plug it into some function, and out pops some number f of x. Then if you take that and plug it back and plug it into its inverse function, it returns you to where you came from, right? Right? You do something to it, and so you put on your socks, then you take off your socks, you end up back at your feet, right? This is kind of like the same thing, but now instead of talking about functions, we're talking about operators, right? Remember from the beginning, we said that, and I said it just a minute ago, that it's these are linear operators, but an operator is something that takes a function as an input and gives you back a function as an output. It's a function that takes functions. There's more to it than that, but in our class, we're just going to leave it at that. So an operator takes a function and gives you back a function. It's a function whose inputs and outputs are functions. The integral is an operator. It takes a function and gives you back a function. Derivative is an operator, and it takes a function and gives you back a function. Are they inverse operators? Looks this way. And if you remember when we first talked about this, your brother asked, this is in Algebra 2, your brother said, like I said, okay, anytime that you're trying to find out are these two functions inverses of each other. So let's say we have x minus 1. I claim that the inverse of it is...
You swap the inputs now.
Yeah, I claim it's x plus 1. And the way to check is to do the composition and see if you get back an x, right? We're gonna compute this right here, and it should give you back, right? That's the whole idea of a function, is that, and an inverse, is that you plug in something and you get out some output, and then you undo that, it should take you back to where you start. It should take you back to x.
Yeah.
And let's just see that. That's f inverse of f of x was x minus 1. But f inverse says you take whatever the input is and you add 1, so you get x minus 1 plus 1.
Yeah.
I said, okay, we're not done, because we have to check if the other way works. And your brother asked, well, if one way works, doesn't the other way always work? And I was like, no. But why am I saying that? And let's just check, because it works in this case. And I said you always have to check. Okay?
Yeah.
And so, okay, you take this, plug it in to the original function, minus 1, so that goes in here. It gives you back x. Ah, you're good. And Josh is like, well, couldn't we just do it with, like, if it works one way, wouldn't it have to work the other way? And I was like, no, something's telling me. And I think we might have done an example with the square root of x.
Oh.
Right? Because that doesn't always work. Like, if our f is x squared, then f inverse, it's kind of like that, but it doesn't always work.
It could be
Because if you compose,
negative.
if you do it this way, right, if you do f of x and then f inverse of x, it might not work, especially if you go -2, that ain't gonna work, right? Because -2 gives you a +4, and then you do your inverse of that and you get +2, so it doesn't work. But what was actually, so does everybody get that?
Yes.
What I just said here, right? Plug in, this doesn't work. This does not give you back a -2.
Yeah.
Right, because you square it, you get +4. Plug +4 into here, you get +2 back. Yikes. And that's why we say that the inverse, well, it depends on the sign. So yeah, it works. But something in the back of my mind was like, there's something bigger than that. Check this out. This is what was going on in my head. I was like, I know there's something. It doesn't always work, and you have to check it, because let's do it in the opposite order. Is this true? Is it true that you take the derivative and then you integrate it? Does it come back?
No, because it gets rid of the constant.
Yeah.
No, this actually doesn't work, right? Because you take your function and you take its derivative. Okay, so now you have f prime of x, but the antiderivative of that is f of x plus a constant.
Yeah.
So we do call them inverse operators, but it's not an inverse in the way that you're thinking about it. There's something else. Just like with the square root. It's like, yeah, square root's the inverse of that, but you've got to be careful, right?
Yeah.
So it's just an interesting thing to say. The last thing I want to talk about. There is an integral. Good luck. It turns out, like, I mean, I remember seeing this and thinking, I'm going to try this one.
But just 1/x times sin x.
Well, what would
Good luck.
What would it
And like, you don't have the tools to even begin to hit this thing yet. And when after a couple more sections, you could hit this with the biggest guns you have, and you're not gonna get anywhere. and you work with days and days trying to find an antiderivative of
Is it
this
not
thing.
Why
differentiable?
not? Why can't you just?
Is it not differentiable?
Because
Wait,
1/x would just
sine
be
of x
log
over-
times
Okay.
sine.
So what do you think it might be?
Well, you
just
can't.
1/x times.
Okay,
sine
that's
of
1/x times sine x.
But you can't split up the integral like that.
Yeah.
Oh.
It's multiplication.
It's not multiplication. We're going to deal with multiplication
Oh, right.
in a couple of sections. And there are methods of dealing with it. And you'll see that none of those methods get you anywhere close to getting this thing. You just keep going around in circles.
So is it not different? Wait, no, it is different. It should be, right?
That's a differentiable function. It's an integrable function. It's perfectly good. This is just sine x.
Yeah.
It actually
Except you can't.
does this.
Zero, right?
It's perfectly fine. It's
But you
perfectly
can't
good
put
to
it in
integrate.
zero.
Yeah, you can.
You could have 1.
What's the limit? What's the limit
Oh,
of sine x over x as x goes
It
to
was
0?
It's just.
It's a big fat
Zero.
1.
Yeah.
It's a big fat 1. It's fine. It's a perfectly integrable function. Nothing crazy happens at all. And in fact, you could define this as a function of t by going from any number, but let's just say 0 up to t. Or you could make this a dt and make that an x and that an x, right?
Yeah.
I mean, like, you can make it sine t over t dt and integrate up to x.
Yeah.
So now you have a function of x. And this thing is actually called a Fresnel. Fresnel, but no, Fresnel integral.
Where the t is the.
t is the input
For the function.
for the function.
But it-
Yeah. But just thinking about this thing in and of itself, say, well, there's not like an antiderivative. Like what? So if you're thinking about it like this, it's like, well, what's that original derivative?
Is there? What is it? How do you?
But check this out. Sine x is x minus x cubed over 3 plus
Oh.
x to the
And then
over 5, and so on and so on, all divided by x.
and then the x's cancel.
And now the x's cancel, so you get 1 minus x squared over 3 factorial plus x to the 4th
And then you
over
can-
5 factorial minus x to the 6th over 1 more is 7 factorial, and so on. Now here's the thing. You have infinitely many things. Can we just integrate each one of them individually?
Yeah.
Yes.
Right?
It's like
Can you not?
So that's one of the things that, one of the questions that analysis answers. It turns out, not always. You can't always do that. If you have infinitely many things, you can't just go and integrate each one, unless your function is what's called... So, again, a sum of things, it can either converge or diverge, right? If you have an infinite sum, right? Whatever the word is. If it converges, right, this is kind of the question about an integral, because an integral is an infinite sum, right?
Yes.
And so now you're taking an infinite sum of an infinite sum. It turns out it's not enough for this sum to just converge. It has to be what's called uniformly
Integral.
convergent. If this sum is uniformly convergent, then you could say that this is the same thing as integrating each one. It turns out this sum is uniformly convergent. So you're good.
Is there a way to write it that's not a Taylor series film?
No, and that's what I'm getting at here, right? So that like you have some f of x. And so now let's do this. Let's find a formula. What's the antiderivative of this?
X.
Okay? Antiderivative of that.
Minus 3. No, 1 over 3. X cubed over 3
So
factorial.
x cubed, so it would be 3 times 3 factorial. Okay, plus
5 over 5 or 5x to the 6th.
x to
X to
the
the fifth.
no, x to the 5th
over 5.
Oh yeah, fifth. Over 5
over
times.
5 times 5 factorial minus x to the 7th
over 7 times
7
factorial.
times 7 factorial, and so on all the way up to negative 1 to the...
N plus 1.
Yeah, something, we're going to work on that. X to the...
To the
N plus
2n
1.
plus 1
2n
Right, because that's
plus
yeah,
1
over
2n
n
plus 1.
times
And 2n plus 1 times 2n
2n plus 1 times 2n plus 1 factorial. Yeah.
And then yeah, it alternates, and maybe our n is off. Who cares? And so, if it's off, we make it a
I think it's
minus
just to
1.
the n,
But
because
there
it
you
starts-
go. There's your function. And again, now we've run into something else. It has no closed form solution. Like there's no way of just writing this thing without doing this. But that's kind of interesting. You can try and find an antiderivative, and it's wicked hard. Because you're going to learn...
So the slope of that function is sine
The
of x.
slope of this function is sine x over x. So if you were to go on Desmos and plot this, right? And you could, right? You could tell Desmos, hey, do the sum as k goes from 0,
yeah.
0 up to, and we big capital N, and above that we go big capital N equals like 5. And then it gives you a slider, so you have a slider for N. Then you could do this and say, okay, negative 1 to the N, when it's 0, it's positive, so yeah, 0, x to the 2n plus 1 over 2n plus 1.
Would it be k though?
Thank you.
Wait.
Now I'm in. So 2n plus 1. factorial. You tell it to do that and plot that. And it'll plot this thing whose derivative is this thing. That might be interesting to do. Go ahead and do that.
So
and
you
then
could say
you
f
go
of x
and
equals
say,
that. And then if you said f prime of x, it would give you sign.
yep, you could do this right here. And then do f prime, then graph y equals f prime of x, and then graph that guy right there. And see. Now, depending on how big n is, it's going to work for some stretch, but not for others. But the bigger n gets, the more this thing is going to look like that thing right there. So that's just interesting. So just something to know, like, you know, that if you're integrating an infinite sum, it may or may not converge. Or it may or may not be just junk that you're doing. So what's the integral of cosine x?
Negative sign. No, just sign.
Yeah, right. Plus a constant. Now let's just check this out. Integrate 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial and so on. Do each one of these individually because this turns out to be uniformly convergent.
Yeah.
And so on and so forth. And we get, let's see, antiderivative of 1 is x. Antiderivative of this would be minus x cubed. 3 would have to go into the denominator, so that's 3 times 2 factorial, which is 3 factorial.
Yeah.
Plus x to the 5th power over 4
X to the 5th.
factorial. It would be 5 times 4 factorial, which would be 5 factorial, and so on, which indeed is sine.
Yeah.
Plus a constant.
What kind of functions aren't
Uniformly convergent. I'm trying to think of an example. I don't remember. They're nothing like they would be defined by their Taylor series or by in series form. But there's not like log is fine, e is fine. Like it's functions that are defined by a Taylor series. Okay. So like if I were to just say, let me just define a series. Here's my function, and it does something like this. X plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 and so on and so forth. Now this may or may not be uniformly convergent. My intuition is that it's not uniformly convergent. One of the telltale signs is look at its derivative. 1 plus x plus x squared plus. That ain't gonna work everywhere. You can't plug in a 1, you can't plug in a 2. You can plug in a half, and that's gonna be fine. So in other words, this function's derivative blows up outside of this interval. And so right around here, you're going to have problems with this original function. It's going to look weird. Its derivative's going to blow up. If its derivative blows up, it's probably going to blow up too. And so you have problems there. So then it doesn't converge here, right? Like it might be perfectly well here, but yeah. And so like this type of thing. Well, it's not just uniformly convergent. Uniform convergence has to do with, given any interval, does it converge on any interval? Like this is fine right here, but it ain't out here, so it ain't uniformly convergent. There's more technicalities than that, and I forget exactly what it is. But that's what it comes down to. You can't just integrate an infinite series if the series itself doesn't converge uniformly, whatever that means. I don't remember. I threw all that stuff out of my head. That's when it starts getting like, oh no, this crazy definition. So, you got homework 25. I need your homework 24 and extra credit next time. And as soon as I get your extra credit, I will post a video on the solutions to the extra credit.